Okay, so what we saw was that dominating set when parameterized by the solution size is W1 hat. Okay, so what about dominating set in directed graphs? So now before saying anything about dominating sets in directed graph, first we have to define what we mean by dominating sets in directed graphs. So we will say that a vertex in a directed graph, a vertex u dominates another vertex v. There is an edge from u to v. Okay. So here u, just this edge that is present, then u does not dominate me. Here we are defining directed notion of dominance. Okay. So in directed graph, we say that a vertex u dominates another vertex v if there is an edge from u to v. So here u does not dominate v. Okay, and in general directed graphs can have both arcs, like from u to v as well as from v to u. So now can you say anything about dominating sets in directed graphs? What? Exactly, right. So if you replace every edge by two edges, so if you have an edge uv is an edge, put an edge from u to v as well as from v to u, right. So you get a directed graph. Okay. So now using this simple reduction, you can show that the original graph, the graph g comma k is a yes instance if and only if the directed graph that you constructed has a dominating set of size k, and this is an if and only if condition. Therefore you gave a simple polynomial time reduction. So the problem is also W1 hat. Okay. So now let us look at one very special kind of directed graphs. So you may also have heard about it previously, which is called tournaments. So what is a tournament is? Tournament is between every pair of vertices you have just one edge. So notice that your reduction heavily relied on the fact that you add edges in both directions, right. So it won't work if you just add edge in one direction. So you were replacing each edge uv by an edge uv and vu. So this is why your reduction was working. So now if I put the condition that no, this you cannot do, right, because and let us give more structure. We know that between every pair of vertices there is exactly one edge. So for every pair, it cannot happen that between some pair u and v there is no edge. There will be an edge and there will be exactly one edge, either uv or v to u. Okay. So this problem, can we find a dominating set of size k? Okay. So this is the question that we will focus on. So before that, we will use a property that, so if you look at any, okay, we will show that if you look at any tournament on n vertices, then it always has a dominating set of size at most 1 plus log n. Okay, and this will be, so notice in tournaments you can compute dominating set of size. Okay, we'll come to this later. For that, for now, let us focus on this problem, that how do we prove this statement. Okay. So we don't want an algorithmic proof, but any proof will do. We are just proving a combinatorial bound. So any idea how we can proceed? Can you apply any, the most basic kind of techniques that you use to prove anything from starting 12th standard or something, 11th or even before? Okay. So, okay, so let us do induction on the number of vertices. Okay. So if you just have one vertex, then there is nothing to prove, right? It has a dominating set of size 1 plus log. It has a dominating set of this size. Okay. So now let us assume that the statement is true for n equals to t, and let's try to prove it for n equals to t plus 1. Okay. So n at most t, and let us prove it. We want to prove it for n equals to t plus 1. Okay. So what should we do? So suppose given t plus 1, let us pick, let us count how many out, let us count the following thing, summation of, so in directed graph notice that if you are given a vertex, there are two kinds of degrees, out degree and in degree. So in degree is counting the number of edges that come into V, and out degree is counting those edges which are going out of this vertex V. Okay. So this is what we mean by, this is in degree. So here it is 3, and these will contribute to out degree, which is here 2. Notice that, look at any arc in this directed graph, it has exactly one, it contributes 1 to the in degree of a vertex and exactly 1 to an out degree of a vertex. Okay. So let us see this thing. So if we count, so look at V in Vg, look at out degree of, okay. So let us look at this number. How many arcs do you have? And choose 2, because between every pair you have an arc, right? So this and notice that every arc contributes 1 to the out degree and 1 to the in degree. Therefore, even this thing is something like n into n minus 1 by 2 or 4, 2. Just a minute. So we have, look, we have these many arcs, look at, it's not, look at any arc, okay, it contributes exactly 1, so it is not 4. So every arc contributes to 1 out degree, right? So this is why it is exactly the number of arcs. What? Exactly, this is why, right? So every arc contributes 1 to the out degree of some vertex. So this, okay. So no, we have to. It's n into n choose. It's n to n choose. How many edges are there in an n vertex graph? It is n choose 2, which is n minus 1 by 2. In an undirected graph? Or no, we are looking at tournaments. Tournaments has exactly one arc between every pair of vertices.
Yeah, my idea was that we divide by 2 because we count every edge twice.
No, 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 no. This is just combinatorial. Combinatorial.
N choose 2 was relevant because we were.
So, but we are putting arc in only one direction. So there cannot be.
There is no scope for double counting every edge.
No, that is not because of double counting.
Okay, then we can revisit this.
Yes. Okay, because look at every pair and arbitrarily put an edge between them. This is what we are doing. If both direction edges would be allowed, actually it would be twice. Okay. No, but the point is, look here, why, look at how many edges can be there in an n vertex graph. How many? Yes, it's a it's n choose 2, right? There can be at most n choose 2 arcs, and in tournaments there is exactly one arc between every pair of vertices. So then the number of arcs is n choose 2, right? This is why. Okay. So you have the summation of out degree is exactly this. Okay. Now what does this mean? So you have n vertices in a graph. Okay. We can revisit this. Otherwise, you will end up missing everything else, right? Okay. So, but it is not very difficult to see. Okay. Okay. So we know that this property holds. Okay. So, but note that there are n vertices in the graph. Okay. So what does this tell us? So there must be a vertex which has out degree at least n minus 1 by 2 by pigeonhole principle, because if every vertex has at most this much, then it can be, if every vertex is less than this much, then it will be strictly less than n minus 1 by 2 into n out degrees, right? But this will contradict this statement. So there is a vertex, right? There is a vertex which has out degree at least this much. So what we know that there exists some vertex u whose out degree is at least n minus 1 by 2. Okay? Okay. So now we will denote this set of vertices by u plus. Okay? So notice that if I select u in my dominating set, okay? So suppose I put u in the dominating set. This will end up dominating all these vertices. How many vertices are remaining in the graph? Right? You at least remove one vertex, right? Right? So you will have strictly less than n vertices. But in that graph, so actually you will have the number of vertices that you will have is n minus 1 by 2. Number of vertices, so look, you had n vertices, okay? So you remove this vertex u because you put it in the dominating set, say these are already dominated, so let us remove them as well, okay? So how many you removed here? At least n minus 1 by 2, okay? So these many vertices will be there in G minus u union u plus, right? What is this number? This is like n minus 1 minus n by 2 plus half. So this is like n by 2 minus half, right? So what? This okay, right? This same as this. Okay. So now of course these are numbers. So you have at most this. So because the vertices cannot be fractions, so the number of vertices is at most n by 2. Okay. What do we know here? We know that this graph has a, so now you have look at this G prime. By induction hypothesis, you know that G prime has a dominating set whose size is how much? Okay. And to create dominating set for the whole graph, you have added this vertex u also, right? So what is the dominating set that you created for G, that we created? It has size 1 plus 1 plus log n by 2, right? Okay. So now what we need to do is we want to bound this number by 1 plus log n, and then we'll be done, right?
Why do we need induction? Like, as in, you can just again say that the
Yes,
rule is a total.
but we look here, then you will end up proving some order log n. Can you tell me the exact number? Yes, you are doing recursive, right? So to be more formal, this is how you should prove, right? Because I am saying a specific number. When you say log n, is it log n or log n plus 1 or log n plus 2? Is that very clear to you? I don't think so, right? To begin with, it's not that clear. So when you're formally trying to prove that this is the concrete number, then it is better to start with induction, right? That's it. So now try proving this. This is not difficult, okay? This an easy thing to do, okay? Right. So now what we have shown is that if you look at any tournament on n vertices, then it will have a dominating set of size at most 1 plus log n. Okay, good. Okay. So we are. So what does this mean? Like, the goal will be to say something meaningful in tournaments as well. So of course we are introducing all these tournaments and dominating set. We have introduced these things here because we want to say something meaningful about this problem. In particular, we want to make some statement about its hardness. Okay. So basically we would like to come up with some gadget and reduction which will help us conclude that dominating set on tournament also is W1 hard. Okay. So for this gadget, these objects will turn out to be very useful. Okay. We have not, this was just combinatorial proof, but we will see what we can do more. Okay. So there is also an object called paradoxical tournaments, which will be quite useful. Let's see what they are. So basically K paradoxical tournaments are those which do not admit dominating sets of size K. Okay. So like look, we have shown that if you look at any tournament, it has a small sized dominating set, in particular of this size, right? So when we are creating our gadgets, somehow this information should be encoded. Like we cannot have K which is something much larger than say log n, because we always know that such a solution will always exist, right? So we have to keep this in mind when. So there is a known for every n which is greater than equal to 2 into 2 to the k into k square, that does not has a dominating set of size k. Okay. So can we find such objects? Is there a way we can find such an object? Does anybody see any way? So given this statement, can we find such an object? This is the question. So what this statement is saying that for pick any n which is this much, then there exists a tournament that does not has a dominating set of size k. So suppose I give you a k, is there some way I can compute such an object? So given the guarantee that there will always exist such a thing, the matter is about, can you find it? Can you find one such object?
Take n equal to this much and then take all the possible directions, one among them, one of the tournament players.
Exactly, right? So what she is saying is, look, even if you are not with this object, you don't have to worry. You can construct it in some f of k time, these kind of objects, right? What do? Take n exactly equal to this, okay? Try all possible orderings of the arcs here. How many such possibilities are there? So how many arcs are there? There are n minus 1 by 2 arcs, where n, fix n, let me denote it by n star, and let's fix n star to be something like 2 into 2 to the k into k square, okay? So now how many possible arcs are there? So for every arc you have two choice, right? So there are at most these many distinct tournaments, right? You can enumerate all of them in time bounded by this, which is some, given such an object, you can find such an object by enumerating, okay? So we will see that why such a thing is useful. Okay. So we will use this object to give a reduction from a problem called set cover to dominating set. Let us see what set cover is. So in the set cover problem, your input is universe U and family F of an integer k. The question is, does there exist a subfamily F prime subset of F where the subfamily has size at most k, that if you take the union of this sets in the family, then this covers the whole universe. Okay. So can you see an easy way in which you can say something about this problem set cover? You have seen few problems, right, which are hard, which are W1 hard. Can you say something about the set cover problem? So maybe you can try it as an exercise. Try showing that this is also W1 hard. Okay? But does any, you have seen recently many examples like, okay, how?
You take the neighborhood.
Okay, so what she is saying is, so suppose we are given a graph G, okay, then we are given vertices here. So but what you want to reduce to what?
So we want to reduce the dominating set to set.
Okay.
So here the sets, the universe is set of all vertices.
Okay, U is V of G.
Yeah. And the family is for each vertex include a set which has V and neighbors of it.
Okay, so the family is okay. So why is this okay? So you, and you take the same k or you take a different k? Same k. Okay. So why is this, what did you say? Okay. So why is this okay?
So if you have a dominating forward direction is clear.
If you have a dominating set, okay, so then the closed neighborhood will cover all the vertices, so it's a set cover. Okay, so you take, so when you take V, you take the corresponding set FV, let us denote by FV. Okay, so take these sets, you have k sets which cover the whole universe. Now why does the reverse direction hold?
In this direction you just see the sets and their corresponding vertices.
Exactly. So look at whatever sets are there, each set is this FV, pick all those vertices in your dominating set. It will dominate everything, right? Okay. So by this simple argument we know that this problem is also W hard. So now we can try reduction from this problem. So now we have we want to go from set cover to dominating set on tournaments. Okay. So here let us consider an instance this thing, and we would like to create some instance, a tournament T and T set some K pi. Okay. So let's see how do we create, we give such a reduction. Okay. So we'll start by computing actually this. So what it is saying is, so and okay, for some reason we'll see later why we need k plus 1. This is for some technical reasons, so we'll see that later. Okay. So what we want to do is we want to compute plus 1 as a parameter. So basically the graph that you will obtain here, the director graph, will have no dominating set of size k plus 1, right? We argued that such an object can be computed by enumeration. By if you enumerate all possible such digraphs, and there will, by this theorem you know that there exists one, so you will be able to find one by enumeration. Okay. So let us compute this object for k plus 1, and we will denote this object by S. This which is this is a tournament on k plus 1 vertices which satisfies this property that it has no size k plus 1. Okay. Is this okay? Here, look, we know that this the guarantee starts existing from n equals to this number also, right? So with the number of vertices equals to 2 into 2k into k square. This is why. Okay. So we create one such minimum sized object, and we have a guarantee that it has at most this vertex. It holds for every n. So in particular it holds for this value of n as well. So for this many vertices, that is 2 into 2 k into k square many vertices, we check if there is a digraph, and we know that there will exist one, so we can find one. Okay. So we have computed then that, and we call it S. Okay. So this what, so I'll denote size of S by I will denote size of S by R. Okay. So what we do is, now let's see how using this object we can create our reduction. So notice that here already we have spent lot of time, right? Because you were enumerating certain objects. But this is still okay because we are still using FPT amount of time. Look at how by our previous argument, when you enumerate, it is still function of k, so or function of k plus 1, still we can manage, we will manage to compute such an object in FPT time. Okay. So let us see what we should do next. So we have universe U, and we have this family of sets F. Okay. So for every, firstly for every element in the universe, so okay, so for every set X family we will create one vertex. Okay. And we will denote it by vertex, which I denote by the vertex subscripted by the set. Okay. This is what I create. Now what we do is, for Just a minute. Now we'll see how we encode the universe. So to encode the universe, what we'll do is for every element in the universe, we will create these many additional vertices. Okay. So look at a vertex in U. So U initially had size say n, and for every such element in the universe, we are creating multiple copies. And how many copies do we create is? We create R many copies. Okay. So look at this element E, and size of the an element say J in size of. Okay. So then we have a vertex here which looks like V E comma J. So for every element in the universe, we create multiple copies, and how many copies we create is given by this R, the number R. What is S? S is the kind of the total that we obtain. These many things here. So we have set. So we will interpret this sets in. We will interpret the partition of this sets into two in the following ways. Okay. So first partition can be based on the elements of the universe. Okay. For every element, I created these things, right? So one interpretation of a partition could be for every element I have these things, and another interpretation could be that for every j I have universe many elements. Okay, so the goal is here. So look at this thing. So for every element from the universe and for every vertex in this tournament, you have a vertex. So actually you are creating in a sense universe many copies of the vertices of this graph, right? Okay. So now the goal would be to encode between this parts we will encode this graph S. So here we cannot encode, but here we can encode. So when we look at the partition with respect to the vertices from the vertex of S perspective, we will be able to encode this graph S, and we will see why such an encoding can be useful for us. Okay. So yeah, this is the tournament here we computed, right? So we do not compute it with respect to k, but k plus 1. We will see why we need k plus 1. Okay. So this is that this is the tournament that we obtain. Okay. And okay. And what we are doing is for every element here we create these copies. So we have created the vertex sets, and we will always remember these partitions. Okay. So how write it like V indexed by W, where W be interpreted like this partition. Similarly, when we are interpreting in column wise, we can index it by V E, right? These are the same vertexes. So if I take union based on the elements of the universe, I will get all the vertices that I created. If I take union row wise, then I will get the whole vertex set. Okay. Is this okay? So I have created all the vertices that we required. Oh, okay, one more vertex will be there, which is V star. Okay. So what will be the purpose of this vertex is, so here we have this vertex, new vertex V. Everything. Okay. So notice that V star, why do we add V star first? We want to choose at most k vertices from F, right? Because these vertices corresponds to sets in our set cover instance. So here I want to choose k things, okay? And this k things in a sense should dominate everything else. But now there will be, if I select some k things here, there will be other things which will remain. They also need to be dominated. So who will dominate them? Okay. So these things will be dominated by this additional vertex V star that we have added. That is why we, so even if we select some k things from, because we want one-to-one correspondence between the solution here and the solution here in a sense, right? So suppose we selected k sets, so we would like to select the corresponding k vertices here. But now we have more vertices here, so these vertices will cover the universe. But who will cover them? The remaining, the vertices corresponding to the remaining sets. So to cover them, we have this additional vertex which is adjacent to everybody else. And note that we will not make any in neighbor of V star. So V star must be a part of the, must be part of every solution, because otherwise nobody can dominate V star in this directed notion of domination. Right? So V star must be part of solution, and we don't have to worry about other things here. So now basically if we choose k things here, we want it to dominate the whole universe, which will be the other vertices, and then we'll be done. Okay, so this will be our goal. This is why we add this extra vertices. So and no, of course we have to do more work, because eventually we want to create a tournament and not just a directed graph, because for directed graph we have already shown that the problem is hard. Okay. So now let us see what other edges we have. So let us look at let us look at any such set and look at the elements that it contains. Okay. So what did I say? So notice that if I select a set in my set covered instance and I select the corresponding vertex, it should whatever elements it is covering in the universe there, it should be dominating here if I want some correspondence. So what do I do is, I add, suppose it contained this element, I add an edge between every such vertex that I created corresponding to that particular element. So if, and this happens only if the set contains that element. So look at an element E from the universe, if, and look at a set F, if this set contains this element E, then I add this edge. So in a sense, if we go back, that set can cover this element, and here when we come here, then this, the vertex corresponding to that set can dominate those vertices, right? Okay, so this is why we add such edges. Okay, now notice that we also have to create edges between this and this. Okay, and I don't want this to dominate these things, because otherwise we know that V star is in solution, and like if V star manages to dominate them, then there is nothing remaining, right? How will we show the equivalence? So this is why, but I need some edge, right? So what we do is we add, so for every such vertex we add an edge from here to V. So we needed some edge, right? So yes, they may be dominating V star, but it's okay. Okay, so we add such reverse edges here. Okay, so we have and what all have we encoded? So with respect to V star, I have told you the edges between these things and between these things, right? So what all edges are remaining? Okay, so edges between them is remaining, edges between them is remaining, and there are edges between here also, some edges are remaining here also. Okay, so this I told to add an edge of this direction if this set, look at this set F, it contained this, if it contained this element E, then we added such edges. What if it does not contain that element? I need some edge in that case also, right? Because eventually I want it to be a tournament, right? So what I do is look at all those elements E prime which do not belong to F. So suppose this is such element, so in that case I add the reverse arc, I add this edge. Okay, so what all I have described? So I have described the edges between V star and everybody else. I have described completely the edges that go between them. So what is remaining to describe is the edges between them and the edges between them. right? Okay. So, but in F, just arbitrarily add any edge, any direction edge, we do not care. Okay. So, this is what we do. So, here we want to create some, we need to give some edge because it has to be a tournament. We arbitrarily add edges and complete it. Okay. So, now what is remaining is edges here in the U part. So, how do we do this is, so inside each part, so now we will interpret it as the partitions like this. Recall that we have two types of partition, one with respect to the universe, which is this oval sets, this partitions this vertex set in terms of the elements of the universe, and the second partition is in terms of vertices of S, right? Okay. So, here let us interpret in terms of vertices of S. Then recall that S is a tournament. I will try to copy the same edges here. Okay. So, notice that I will so look at pick the copies here. Okay. So, I add an edge between them, pick some vertices like this, I add an edge between them if I preserve the direction. So, if this is say vertex W1, this is W2, and W1 and W2 are vertices of S. Okay. If the S direction is this, I add an all edge between them and then directed from the top one to the bottom one. If the edge is like this, then I direct everything in this direction. Okay. So, what we have done is, I have also described the edges when across these things. So, only thing I need to describe is what happens in this oval part. Just a minute, okay. Yes. So, because I have told between them, right. So, and I have not told what happens here, right. Here just arbitrarily add the arcs in any direction. Okay. So, what did I describe? I described across. So, what is remaining is inside that part. So, inside that part we add edges arbitrarily. Okay. And okay. So, this is the reduction. Okay. So, now we also have to set the parameter. So, if we had g comma k, then we set it to be this g prime comma k plus 1. Okay. Now, we want to show that, we want to prove that the instances are equivalent. Note that this is an FPT reduction. Here we actually used FPT time because we needed to compute this object. Okay. So, let us look at the forward direction. So, suppose we have, so suppose I have, so this was U and this was F, and suppose I have some sets here which together cover the whole universe and it is of size at most k. Okay. I take the same vertices here, okay, and I also take V star. Let us see if it is a dominating set. Okay. Notice that because the way we have added the edges between this and this, because here this subfamily F prime is a solution for every element in the universe, there is a set which contains it. So, in particular, if you look at any vertex here, right, there is a set, there is a vertex that dominates it, because that is how I have added the edge. So, if it dominated, okay. So, now I add also V star. So, if I put V star, all these things are. So, I have obtained a dominating set of size k plus 1, right, in our tournament. Now, now we want to see the reverse direction, right. In the reverse direction, what we have to show is, if in this tournament you have a dominating set of size k, then I would like to construct the some subfamily F prime which is a set cover. Okay, that is, if I take the union of these sets in this subfamily, then I get the whole of the universe. Let's see how we can do this. Okay. So suppose, so I can rub this, I think everybody will remember the definition. So let us take the subfamily F prime to be, so just take, yeah,
Suppose there were two vertices,
yeah,
W11 and W12.
W,
In W1 row, you have made a row, right?
yes,
Okay, two vertices.
okay,
So W11 is dominating everything apart from its own graph.
W, why?
Because you said that how you didn't, you said that you arbitrarily add an edge. How are you adding the edge crosswise?
Crosswise means here,
No, no, here.
here.
No, this and vertices of diagonal. Not between the vertices that you see this particular point.
So let us call this VW and this is VW2. So do you mean between this, or do you
One. So go diagonally.
so which is the part indexed by W, or is the part indexed W2?
Okay, and second vertex.
This one,
Yes.
okay,
Okay, first one.
this one,
Yeah.
yeah.
So you said arbitrarily edge.
No, here it is not, just a minute, here it is not, just give me a minute, okay. So here, look, I described how to add edge between this part and this part by this S, because look at the number of these parts that we have. This is same as the number of vertices in S. How many rows are there?
Okay, so
So let me call this W1, W2, Ws. Okay. What are we doing? So for every vertex E in the universe, I created S many copies, size of S many copies, okay? And this I do for every element in the universe. So look at, if I, so this oval thing represents the copies of the vertex corresponding to the element of the universe, okay? So if you look at the number of rows, that is size of S. And the way I add an edge between two rows, two distinct rows, is I just see how this edge looks in S and I just copy it. Here it is not arbitrary, okay? Right? Okay. So now where were we? So now we were looking at the reverse direction. So what we have is, we have a dominating set of size k plus 1 in our uh, the tournament that we created. We wish to create a family F K. Let's take this one first. So let us take F prime, which is F says that, the family F says that UF below. So let us pick a dominating set. D is a dominating set in our tournament prime. Okay, G prime is this. Okay, so we know that D has size at most k plus 1. So where UF belongs to D. So, or in other words, what I can say is, so this is I hope this is clear that UF are these vertices corresponding to the family, okay? So this is what my F prime is. Firstly, I need to show that F prime has size indeed k, right? Because I start with a dominating set of size k plus 1. So maybe it happens that F prime has size k plus 1, right? Who has stopped me picking k plus 1 vertices from here? Okay. So notice that no vertex that I added from this vertices corresponding to the universe, they can dominate V. So V star can be dominated either from here or here. It cannot be these vertices UL, which means that there is one vertex, at least one vertex, which is outside of this thing, which is responsible to dominate V. This is, look at that vertex, okay? That corresponding to that vertex, I have not added any set in my family. Therefore, we can say that the size, okay. Although I start with a dominating set of size k plus 1, because V star should be dominated by somebody, that somebody has to be either V star or somebody from this the vertices corresponding to the universe, okay? It cannot be here. And the way I have created this family is only based on the vertices that are selected from here. Therefore, there are only k such vertices at most. So therefore, this family f prime that I have created has size at most k. Okay. So now size is okay. What we need to show is that it is also if you look at this family, it forms a set cover, right? So if it already forms a set cover, there is nothing remaining to prove. Otherwise, there is some element in the universe which does not belong to any of these sets, right? So we are going towards a contradiction. So if the property is already satisfied, there is nothing to prove. But now we are assuming that there is somebody in the universe. So look at this, this is universe and these are my families, these are my families from f prime. So there is an element E which is not contained in any of these sets. Otherwise I will be done. Pick such element, that element E, okay? And let us look at how element E looks here. Okay, so I'll zoom this U part here. So we have, so suppose this is this part E, the row that I have created, let us index it by VE, okay? And here I have this partitions like this. Okay. So notice that if you look at the number of vertices that I have created is quite elements in a column, it's 2 into 2 to the k into k square, and I just have dominating set of size k, which k plus 1, okay? And now let us see, so this has at least, these has this many elements, but what do we know? If you look at this part, okay, let us pick one vertex from each part, okay, from each of the rows. If you take this thing, then look at the graph induced on it. How did I create this graph? This graph was exactly created by copying S, right? So the edges present in this diagram, because look, I added arbitrary edges here between two rows, I added between columns, right? So if you pick one vertex from each of the rows, look at the diagram that I get. This is exactly same as D, because that's how I have added edges, right? I have preserved the direction. But what property do I know about S? If you restrict this part, you restrict to this part, this alone cannot have a dominating set of size k plus 1, right? Maybe, of course, there can be some crazy vertex outside which is dominating everything here. That is okay. But we know that, but we know that if you restrict your digraph to this portion, this alone does not has a dominating set of size k plus 1. Okay? Okay, good. Then okay, let us create the set Z as follows. So Z is the set of all those vertices which belong to S. So is that So let us pick, what do we mean by this? Let us interpret this, okay? So look, when I write like this, I'll use this, okay? So I'll index, here you have element E1, E2 up to element En, and these things I write like V of W1, V of W2 and V of Ws, okay, size of S, where these correspond to the vertices and these correspond to the elements, the partition, okay. So what is this saying? So we look at S, okay, I collect in Z those vertices of S, look at the corresponding rows, okay. Notice that the number of rows is this much, okay. I am collecting some at most k plus 1 rows here which intersect with the dominating set. So just collect those rows and keep it here, okay. This is also not a dominating set for Z. This Z is not a dominating set for S because size of Z is at most k plus 1, right. Because Z is not a dominating set for S, there is a vertex in S which is not dominated by Z, okay. So this graph is S, we chose a Z here, there is a vertex W here which is not dominated by the set Z, okay. Fix, is it clear or is this, okay, fix that vertex W, okay. So this vertex I fix. Now notice that so I have a pair, so I have a pair E comma W. What is E? E is from the universe, this W is from this graph S, okay. Now look at this vertex, notice the column that I created with respect to this vertex E and the row that I created with respect to this W, okay. So basically where are we? So this is corresponding to E and say this is corresponding to this VW and VE. So here I have a unique vertex that I have added for this particular index, right. So basically look at the Wth vertex, copy of vertex that I added for the element E in the universe. This is what we mean by this, okay. So now we want to see who is who is dominating this vertex, okay. So note that the way we have added the edges, the vertices in so by our assumption and the way we have added edges, so if I call this vertices V of F, if you look at D intersection V of F, it is not dominated, right? Because if it were dominated, then what does this mean? There is an arc from some set here to this vertex, which will mean that it will contain that element. But we started with an element which was not covered by by this family. So vertices here do not dominate this particular vertex. The vertex that I have chosen is not dominated by vertices here, because this will contradict that element E was something which was not covered by this subfamily, right? Okay, so this thing does not dominate it. Okay, fine. Notice that word, right? If you look elements here, so V star cannot dominate it. Okay, so this also does not dominate it. So now if you look at vertices inside, but the choice of this vertex, it is not dominated, because how did we construct Z? It was those vertices which are in the dominating set, and we chose a vertex which is still not dominated by this Z, which existed by the property of the tournament that we constructed, right? So in particular, inside this nobody can dominate. Now it is outside, somebody has to dominate, but outside who dominates? Let's see, okay. So outside, look at so we know that no, actually we not only know this, we know that no layer vertex can dominate it, because if any layer vertex dominates it, we can pick that one vertex from each row and we still know that it is not dominated, right? So nothing from these different layer can dominate it, okay? And what did we do inside this, right? That is the only thing remaining. Okay, no. So the only thing remaining is this thing, this row, right? Here we have to see what happens inside this row. Good. But wait, in the dominating we are, yes, right, exactly. Okay, so the way we had just a minute, VW, yes, right. In this row there was nobody in the dominating set, right. So this vertex cannot be dominated. So this vertex is not dominated, but this means that the thing that you started with was not a dominating set. Therefore it must cover the farm. Okay. So this was the reduction. Okay. So now we'll see one more short reduction and then we'll stop. Is this okay? So, okay. So now we saw reduction for dominating set. We also saw that if you look at tournaments, then there also the problem is quite hard. Now let us look at connected dominating set. So what is connected dominating set? So connected dominating set, so in dominating set, here we are given graph G, integer k, and Vg, size of x is at most k, and if you look at graph induced on x, then it is connected. Okay, so this is what we mean by connected dominating set. Okay, we'll see that even this problem is hard. So we would give a reduction from, we'll go from the dominating to connected dominating set. So does anybody has a hint? This is not that difficult reduction. That what can we do? So here we are given an instance G comma K. Here we are looking for any dominating set, and here we are looking for a dominating set which is connected. Yes, it is an undirected graph. Okay, so let us see. So what we here is, so firstly we want connectivity property, right? So whatever k vertices we select, the if you look at graph induced on x, it has to be connected here. Okay, if I take k plus 1 everybody, then this graph has a pick one vertex, it will dominate everything, right? So this you cannot do. If you make something, you add something from out.
No, it won't dominate the other k vertices.
Okay, so just pick one more, no? it has a dominating set of size 2. So it won't work. Like take the below vertex and take somebody, because everything is adjacent, right? So then you get a dominating set of size 2. So this you cannot do. So adding something additional globally is disastrous for dominating set of kind of problem, right? Because that new vertex dominates everything, and you are not really dominating, you're actually losing the property that you need of dominance, right? So this does not work. So any other suggestion? Okay, so let's try to do it, okay? So notice that we want it to be connected, right? Irrespective of what subset we choose, we want the graph to be connected, right? So in a sense, what is a graph that you can think of which will always be connected despite what vertex subset I choose? Click, right? So click is one such thing. So let's start. So in a sense, if we want to go from here to here, an easy way to start with would be click, something related to click.
So you introduce a vertex for each UV and make the
What is UV? So we have this graph G. So this is G comma K. We have UV and
No, what I'm saying is you introduce another, like for each edge UV, introduce a vertex.
and do I keep this edge?
No, one, like a vertex for an edge
Okay.
EUV.
Okay.
Now, do this for every edge and make that a click.
Make what a click?
The additional vertex, you make it adjacent to the
So I make these, the original vertices a click or these vertices a click?
Oh, edge vertices. Edge vertices.
Here I clickify, okay? Then I am choosing a subset from here. How does this help in connectivity? Like look, I am given a k size thing which is a subset of the vertex set. So how do I convert it? How do I use this additional vertices to obtain connectivity? Because you have added connectivity on the other side, but you need connectivity on this side, right? Okay. So let's do something very similar, okay? So what do we do is we are given this graph G, G comma K. So I'll draw this on the top. So we are given this graph G comma K. What we do is, so say we have Vg is n. What I do is I create two copies of the vertices, okay? So this I call V1 and this I call V2. These are just copies of the vertex set. I have not introduced any edges, okay? Okay. So here I have n vertices and they are in one-to-one correspondent with the vertex. So suppose I have a vertex V here, I have created two copies, copy V1 and copy V2 here, okay? For every vertex I have this thing, okay? So now I create here a click, okay? Now what I do is, so I don't add edges between the same copies, I do not add this, okay? So look, for a vertex I have two vertices V1 and V2, I do not add edges between them, okay? But what I do is, look at any, so if I had an edge UV here, so look, and first copy of this vertex I add edge. And similarly I also add, so there will be a copy U1 here and so I also add this edge, okay? I do this procedure and the claim is it is enough, okay? Let's see why. What? What did he say? No, it's not labeling. That was a completely different procedure. Because there what you did was you created vertices for edges, not vertices. Here I am creating vertices, two copies of the same vertex, and there I was creating a copy for an edge and I was selecting from the vertex side. So those two things are very different. Okay? So the forward direction is very simple. What do we do is, so we have this, take a dominating set here, pick this set D which is of size at most k, okay. Now if you pick the same set here, it is connected because it is a click, okay. So this direction is trivial. So how do we proceed with the other direction, right? So what do we want? We want some, if we are given a connected dominating set D here, I want a dominating set here also. So
Just whatever vertices like D intersection V2, you can select the corresponding vertices.
is that enough? So D, okay, what did we say? So suppose I have a solution here D. So I want to, so here take it D prime because this is graph G prime. So I want to create a set which is a dominating set in this graph. So what is the construction? What is D?
You just take D is equal to like D intersection V1.
So D is D prime intersection V1.
And then you take the corresponding vertices in V1 which are there in D prime intersection V2 because there are no edges
So
between V2.
yes, so basically what you are saying is, you are not saying this, what you are saying is you take D equals to U such that either U1 belongs to, so U1 comma U2 intersection D is not equal to empty set. Then in that case you take the vertex, right? This is what you are doing, okay? So this is what your D, and you pick just one such vertex and intersection, right? And now you want to say that D is a dominating set in this original graph, right? If it is not, so if it is not, then there is some vertex which is left out, right? It has no neighbor here. But then look, let us come back here. So whatever selected, nothing dominated, right? So who dominated this vertex? If this vertex, so this vertex, look at the copies here and here. So you have two copies, this you have U1 here and you have, I have drawn U2 here. So these are the same copies, okay? So look at this vertex and look at this vertex. Who is dominating them, okay? So if one of them were in the solution, you're done, because then this U would be in the set and then U is dominated trivially, right? So they both are not there, but then you have selected it appropriately. So therefore it is also a dominating set, okay? So this shows that connected dominating set is also W1 hard when parameterized by K.